In this video, what I'm going to be describing is Gauss's law. Now, to start out with, we've previously talked about an individual point charge of plus Q. And what radiates from that individual point charge is going to be electric fields. Radiating in all directions. Radiate in all kinds of different directions. Oops, keep missing that. But this isn't very practical, right? It isn't practical to think of one individual point charge. Typically, what we have is we're going to have some kind of distribution or collection of charges. And an example of that would be a parallel plate capacitor. Now, a parallel plate capacitor is not just one individual point charge. It's a collection of point charges that in between the two plates will be an electric field. But along came Gauss. And what Gauss did is he described a relationship between the point charge distribution and the electric field that's going to emanate from this point charge. However, Gauss's law causes us to introduce a completely new term. And that new term is going to be the flux. And in this case, E stands for electric. And so this is going to be a flux. And a flux involves the electric field and the surface through which it passes through. Now, previously we've seen before where the surface that surrounds the charge has to be circular. That's not the case now. We can choose any surface we want to encapsulate this distribution of charges. And a few things that occur because of this. One is that the electric field does not have to be perpendicular to the surface. Secondly, it does not have not a uniform charge. So not uniform charge. Does not have to have a uniform charge. However, what has to happen though is that this has to be closed. This has to be a closed surface. It has to be entirely closed. So that's a few things we have to look at, that we have to take into account. The electric field doesn't necessarily have to be perpendicular to the surface, and it does not have to have a uniform charge. But the surface has to be closed. It has to be closed. Now, what can we do with this surface? Well, what we can do with the surface is we can cut it up into little tiny pieces. So if we cut that up into little tiny pieces, so let's move that, let's move it somewhere over here. So we're going to take this little piece we have here, take that little piece we got there, and what's going to emanate from that is going to be the electric field. Emanating from that. So that's going to be our electric field emanating or radiating from this point charge through the surface we just selected. And let's say that this is just going to be surface 1. Surface 1, this happens to be electric field 1 as well too. We just cut a portion of it out. We called that surface 1, and now we're just taking a bit of that. Now, normal to that surface, that's our normal, we're going to select the portion of the electric field that is perpendicular to the surface or parallel to the normal. What I'm saying is we're going to select a portion of this electric field that is going to be orthogonal or normal to the surface. And that's going to, and there's going to be some kind of angle between that. There's going to be some kind of angle between the actual electric field and the portion of the electric field we're going to take that is going to be parallel to the normal or perpendicular to the surface. Now, we can write that now as E1 cosine theta 1. That's how we can represent that vector using trigonometry. Now what we can do is we can look at the entire flux through this surface. So if we look through the entire flux through that surface, so we're looking at the flux through surface 1, that's going to be E1 cosine theta 1 times the area of that surface. Now, if we have a lot of these surfaces, excuse me, if we have a lot of these surfaces, right, if we have a lot of these surfaces, we can then write our flux now as E1 cosine theta 1 times our area 1 plus E2 cosine theta 2 times the area of 2. And you can see how this is going to go on and on and on and on and on. Now, let's be kind of clever about this. All right, let's say that what we're going to do is we're going to choose a very small surface. Oops, can't spell very. A very small surface, such that the surface is going to be so small that our theta has to be 90 degrees. It has to be 90 degrees. And so what we're going to do is we're going to now make these areas so small that the surfaces, that the electric field has to be perpendicular to the actual surface. And so now what our electric flux is going to become is, because the cosine of 90 is going to be 1, now our total electric flux now is going to be equal to now E1 delta A1 plus E2 delta A2 plus it goes on and on and on. Such that you can now, and if all these are going to be uniform, it's such that we can now write this as now the summation of I of the electric field. I should put my arrows above that. It's a vector, sorry. Such that now our equation here is going to simplify as such that it just simply becomes the sum of the dot product of, or the multiplication of the electric field times our area. We can say that this will now simplify to the charge on the inside upon our permittivity of free space. So what we've done is we've made what was once a very, very difficult problem into something which is much easier, in that we introduced the electric flux, we randomly chose whatever surface we wanted to choose. We picked out a piece of the surface, so long as the surface is closed, and we broke down the electric field as such. And then we made this surface so much smaller that the angle was going to be 90 degrees. We then summed over all those different surfaces, which is what we get here, and we found out that that is going to be equal to the charge on the inside divided by the permittivity of free space. It really simplifies a very difficult problem.